This lecture is on Chapter 0. This is a review of units, measurement, sig figs, and unit conversion that you should be bringing in from high school. So approaching chemistry. How do you approach chemistry? So chemistry is a physical study of the world around us, and it's about observing the environment using all of our sensors and to look for patterns. And so, if we think about some of the observations that we can make, we can use our sight, our sense of smell, our hearing, our taste, our touch to observe everything that's around us. And based on what's around us, we can look for trends. And when we come up with trends, some things that we see repeating over and over again, we can start to ask questions towards probing and understanding of what's actually happening in our world. And so, this idea, this quest of finding out what our ultimate truth is, has to do with the scientific method. And so, in the scientific method, we develop what are called a hypothesis, or plural is hypotheses. So, after observing trends, we can formulate questions and test those questions and route towards developing a hypothesis. So, a hypothesis is a proposed explanation made on the basis of limited evidence as a starting point for further investigation. So once we come up with a hypothesis or multiple hypotheses, we test those using experiments. And those more experiments allow us to develop more hypotheses, which allow us to develop more experiments over and over and over again as we refine our understanding until we finally develop and we gather enough information and get a clear enough understanding that we can develop what's called a theory. And so a theory is defined as a well-established explanation of scientific data. So theories cannot be proven, but they can conversely be disproven by a single contradictory result. So theories are not laws of nature. They are simply just our human understanding of the world that's around us. So throughout this course and throughout lecture and laboratory, we're going to be getting familiar with collecting data, observing our results, coming up with hypotheses, testing those hypotheses, and coming up with our own theories. And so the purpose of this sort of introductory lecture is to get you up to date on some of the techniques that you'll need to make in order to collect those data and to observe our surroundings and to actually be able to analyze and make sense of those findings. So the first thing we're going to focus on is chemical measurement. So chemistry is an experimental science, which means it requires measurement of substances. So we could be measuring the amount of a substance, the volume of a substance, the temperature, etc. And so we can see some of these different physical quantities that we can measure are listed over here in the table. And so what we have developed as a group of scientists here is a list of established units that we use in order to quantify these measurements. So in 1960, an international agreement resulted in the establishment of the SI unit, which is based on the metric system, which is a set of units here to describe all of these different sort of measurements that we can use. And so all of the countries in the world, except for the United States, Liberia, and Myanmar, use this SI set of units in order to describe their measurements. And so does not make any sense whatsoever why the United States is holding on to this antiquated old idea of ounces in the feet. And it really just makes things quite confusing. And so the more that you start to use the metric system in your experience throughout science, you'll realize that this base 10 system of measurement that was established in the SI system really just makes extreme sense. So let's take a look at some of these fundamental units that we're going to be measuring throughout our chemistry course. So the first unit we're going to look at is mass. And so in order for us to understand mass, we need to first have a working understanding of matter. So matter is defined as anything with a physical presence. So anything that you could touch, taste, or smell. So scientifically, everything has mass. And so mass is defined as the amount of matter in an object. And so the SI unit for mass is the kilogram. But the kilogram is way too large for most of our measurements in chemistry. So we use a smaller set of measurements, grams, milligrams, micrograms, nanograms, picograms, to uh, describe our units of mass. And so we'll get into those prefixes for mass in a few slides. But just sort of for reference for you, 1 gram is a bit less in mass than a US dime. So you might hear some people interchange the word mass and weight for each other. So weight is defined as the measure of the force that gravity exerts on an object. And so therefore, it's dependent on an object's location. So therefore, the weight on the Earth versus the weight on the moon is totally different because the force of gravity is different in both places. So since there's more gravity on Earth than there is on the moon, your weight would be much larger on Earth than it would be on the moon. Whereas the mass, which is a measurement of the amount of matter, the mass is the same regardless of where you're located. So since everywhere on Earth has the same gravity, we can use the weight to measure the weight measured with a balance to assess the mass. Okay, so we actually use weight on Earth to assess the mass, but you have to know that weight and mass are themselves different. Next fundamental unit is length. So the fundamental unit for length is a meter, and so that's equal to 39.37 inches, and it's 10% longer than a yard. And so our understanding of the meter has changed over time, and it has our sort of standard for the meter has become much more well defined as the years have gone on. So, for example, in 1790, a meter was defined as 1/10 millionth of the distance from the equator to the North Pole. Pretty difficult to measure, right? 1889, it was defined as the distance between two thin lines on a bar of platinum iridium alloy that was stored near Paris, France. But there is a problem there. What happens if somebody steals that bar of platinum iridium? Then we would never know what a true meter is again. In 1983, we define the meter as the distance traveled by light through a vacuum in 1/299,792,458 seconds. All right, so that is a value that can never be messed with, and nobody can steal the distance traveled by light through a vacuum. So I thought it was kind of interesting how our understanding of what actually defines a meter has changed over time. But again, these meters are way too large for most of chemistry, so we use centimeters, millimeters, micrometers, nanometers, picometers. Again, we'll get to those prefixes soon. Next would be the fundamental unit of temperature. So the fundamental unit of temperature is in degrees Celsius. And so it's very easy to work with degrees Celsius when we're talking about water. So 0 degrees Celsius is the freezing point for water. It corresponds to 32 degrees Fahrenheit that we use here in the States. 100 degrees Celsius is equal to the freezing point for water, which is 212 degrees Fahrenheit. So many scientific studies will use a measurement of temperature called Kelvin. And so again, this is not degree Kelvin, this is actually just Kelvin. And so it's the same scaling as Celsius, but there's a different 0 point. So whereas Celsius defines 0 as the freezing point of water, Kelvin defines 0 as absolute 0, which is equal to negative 273.15 degrees Celsius, which is the coldest possible temperature. So 0 Kelvin is called absolute 0, where there's actually no molecular movement. So if we're going to convert between our different scales, we'll have to introduce some conversion factors here. So a conversion factor between Celsius to Fahrenheit is degrees Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees Celsius times the temperature in degrees Celsius plus 32 degrees Fahrenheit. You could rewrite this to talk about conversion of Fahrenheit to Celsius by saying that the degrees Celsius is equal to 5 degrees Celsius over 9 degree Fahrenheit times the degree Fahrenheit minus 32 degrees Fahrenheit. So these are known as conversion factors between two different units. And we'll talk more about conversion factors in a little bit. And so if we're talking about temperature in Kelvin, Kelvin is equal to our degree Celsius temperature plus 273.15. And so the important part is the distance between 1 degree Celsius. So 1 degree Celsius, so a change, delta means change. The change in 1 degree Celsius is equal to delta, so the change in 1 Kelvin. So the units of Kelvin and Celsius are the same. So a change in 10 degrees Celsius is equal to a change in 10 Kelvin. But the degree Celsius and degree Kelvin changes do not correspond directly to changes in degree Fahrenheit. All right, the next we're going to talk about are derived units. So derived quantities are expressed using a combination of one or more of our 7 fundamental units. Okay, so for example, area is defined by length times length. Volume is area times length. Density is the mass per volume. Speed is distance per time, et cetera, et cetera. So we have our fundamental units that have been uh, gone through mathematical transformations. And so therefore, their derived units are a little more complex. So some of the common derived units that we'll see are volume. So volume is defined as the amount of space occupied by an object. And so the SI unit for volume is the cubic meter, so the meter cubed. And so 1 cubic meter is equal to 264.2 gallons. So again, this is a ridiculously large value. And so instead we use the unit of a liter, a milliliter, or a microliter. Next derived unit is density. So density is a property relating mass to volume. And it's you find density by dividing mass by volume in either milliliters or centimeter cube. Milliliter and centimeter cube are the same. And so the density, and so the SI unit is in units of gram per centimeter cubed or gram per milliliter. And so density is temperature dependent. So the temperature must be reported with any density. So for example, if we look at this graph here, where the x-axis is the temperature and the y-axis is the density, we can see that the density of water changes depending on its temperature. Where at 3.98 degrees Celsius is actually the highest density for water. And you can see when water gets down to its freezing point, it actually has a lower density. So that's why um, floats in water. The next derived unit is energy. So energy is defined as the capacity to supply heat or do work. And so the SI unit for energy is joules. And so 1 joule is equal to a kilogram times meter squared over second squared. Okay, so you can see that's kind of a cumbersome unit. So that's why they've introduced the joule. So joules are very small. So for example, it takes 100,000 joules to heat up a cup of water to boiling. And so kilojoules are much more frequently used. So that's a joule times 1,000. So another energy unit is the calorie. And so 1 calorie is equal to 4.184 joules. And so it's defined as the amount of energy required to raise 1 gram of water by 1 degree Celsius. And so the calorie with a capital C, so this is super confusing, lowercase c for calorie, uppercase C for capital calorie, is equal to 1,000 calories. So basically it's a kilocalorie. And so that's equal to 4.184 kilojoules. So these uppercase calories are the ones that we're actually talking about when we're discussing the calories of food. Okay, and so it's important for us when we're discussing these different units to have a working understanding of accuracy and precision. So, accuracy is defined as how close a measurement is to a true value, whereas precision is how well a number of independent measurements agree with one another. Okay, so a precise set of measurements are all going to be measurements that are going to be very tightly grouped. Whereas an accurate measurement is going to be a measurement that's very close to the accepted true value. So if we think about this in terms of these dartboards here, okay, so we see for A, all of these darts, if we're throwing for the bullseye in the middle, all of these darts here are very tightly grouped. So we can say that they're very precise, but they're not very accurate because they haven't gotten to our bullseye. Whereas B, we can see they're very tightly grouped, so they're highly precise and they're highly accurate. Whereas for C, we can see that they're not tightly grouped, so they're not very precise, and they're not near the bullseye, so they're really not accurate either. So when we're taking measurements, we're recording different values, and we can some of the values that we're going to be recording in our study of the world are going to be in a large range from impossibly large to impossibly small, and some of the numbers in between. And so we use what's called scientific notation and prefixes in order to express these values in a more manageable fashion. So, for example, the diameter of an atom is 0.0000000000372 meters. That is an inconceivably small number and very, very hard and cumbersome to talk about. Whereas the distance from the Earth is what is that? 150 trillion meters away. And so again, that's an impossibly large value that's very difficult to work with. So if we want to express these two very cumbersome values using scientific notation, it's really quite easy. So first, let's take a look at the diameter of the atom. So 0.00000000372 meters. So what we do for scientific notation is we take our decimal place here and we simply move that decimal place over until we move it past our first digit. Okay, and we count the number of times that we move that decimal place over. So we're moving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've moved that 10 spaces to the right. And so whenever we move a decimal place to the right to make a number smaller, we're going to raise that value now to a factor of 10 to the negative of however many places we move. So this would now be 3.72 times 10 to the negative 10 meters. And so what that means is we've moved this decimal place. So remember, each decimal place that we're moving, this is a factor of 10 that we are changing. So a factor of 10 and another factor of 10 combines together to a factor of 100. Another factor of 10 gives us a factor of 1,000, et cetera, et cetera, et cetera. So what this means is we have moved that value to the factor of 10 to the minus 10 away. So this is scientific notation, and so the negative sign indicates that we have moved that decimal place to the right. Okay, if we take a look at our distance of the Earth to the Sun, we have 150, and then we have three sets of 000s. All right, and so not written here is the decimal place, which comes right after the ones place. And so for this, again, we're going to move that decimal place, but this time we're going to move it to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we've moved it 11 spaces. So in this case, instead of for the smaller numbers where we moved it to the right after the first digit, here we're going to move it all the way right before the final digit. Okay, and so now to indicate that we have moved that decimal place to the left, we will not have a negative sign. So now we have 1.5 times 10 to the 11. And again, this was, sorry, in meters, so we can carry that unit of meters. So this is scientific notation showing how to express very small values and very large values in more manageable ways. And so we'll drop all of these zeros that we're not using. And so you can see that you can carry this scientific notation in any sort of, you can move it any distance that you need to in order to express a whole range of values. So we also have prefixes that can be sort of a shorthand verbal notation of how large or small a value is. So I'm sure you're familiar with a meter. A centimeter is 1/100th of a meter. So a centimeter is zero point zero 0.01 of a meter. A millimeter is 1/1000th of a meter, so 0.001 of a meter. A kilometer or a kilometer is 1,000 meters. So it's a way of sort of multiplying this conversion factor to a value. So some of the common prefixes that we will encounter in our physical sciences are given to you here in red. Okay? So next is our discussion on significant figures. So significant figures are the total number of digits recorded for a measured or calculated quantity. So known values or constants have an infinite number of sig figs. So it's important to know sig figs are only for measured values. So all digits but the last are certain. The last digit is an estimate. So there's an error of plus or minus 1 is assumed. Okay, so what this means is if you're going to be measuring a distance of something using a ruler, okay? So for example, I ask you to measure the distance of this black bar, and I have all of you here watching this video try to measure that black bar, what you're going to do is you're going to say, okay, it's somewhere in between, so 1 centimeter, 1.7, so it's somewhere between 1.7 and 1.8 centimeters. And so you know that with very high certainty. But when you're making a measurement, you need to make an estimate of your final guess between those two. So instead of saying it's somewhere between 1.7 and 1.8, we look at this and say, I think that's about 1.74. Okay? And so that's a pretty good guess based on where we think it is, where we see with our eye. It's much closer to 1.74 than it is to 1.79, so it's a pretty good guess. But if I asked all of you watching this video to record your guesstimate here, it would all be different. So that last digit that we recorded is uncertain because it is a guess. So the purpose of significant figures is it's the amount that you are reporting, and that final digit that you are reporting is a guess. Another sort of illustration we can use for significant figures is if we're using an analytical balance to measure the mass of a substance. And so if we use an analytical balance, it goes down to 1/10 of a millimeter or a milligram. So a very, very tiny amount. And so when you're trying to measure, that last digit is fluctuating slightly with movement of air, with vibrations on the ground. It's a really an uncertain value. So when you report that down to 1/10 of a millimeter, or sorry, 1/10 of a milligram, we know that that final significant figure, that final mass recording is uncertain. So that's the actual purpose of sig figs. So sig figs seem to really annoy a lot of students, but really, once you know the reasoning behind them, it seems much more useful and much more important. Okay, so once we've established how many significant figures that we should report for a measured value, we are going to have to do some sort of mathematical manipulations with these significant figures. So we need to know which digits are indeed significant and which digits are not significant. And so we have four set of significant figure rules for establishing which digits are significant or not that we'll be using in this course. So I know some of you may have had different rules back in your high school or in your previous experiences, but I don't care what you're bringing to this class. These are the rules that we are going to be using. Okay, so I don't want to hear about what your high school teacher did previously. This is what we are doing in this class. Okay, all right, so here are the four rules. So one, zeros in the middle of a number are like any other digit, they are always significant. For example, 4.803, that's a trapped zero. That zero is significant. Two, zeros at the beginning of a number are not significant. They act only to locate the decimal point. So for example, 0.00661, these what are called leading zeros are not significant. And the way that we can tell that is if we rewrote this number using scientific notation, we know that we do not include those leading zeros. Three, zeros at the end of a number and after a decimal point are always significant. So these are what are called trailing zeros. Okay? And so these trailing zeros here are significant. All right, so that is a zero after a decimal point. Zeros at the end of a number and after the decimal point may or may not be significant. Okay? And so, for example, if we look at 34,200 meters. And so heading up to the whiteboard here, we can actually establish the rule of whether those zeros are significant or not. So it depends on how we write this number, 34,200. So the two ways we can write this number are, excuse me, sorry about that, 34,200 or 34,200 and then include a decimal place. If so, the rule of thumb here for number four, the clarification for number four, is if we do include a decimal place, that means that these are now trapped zeros. So we can think of that decimal place as a wall. So everything between our first and our last digit, which will be our decimal place, are significant. So in that case, you have 1, 2, 3, 4, 5 sig figs. If you do not have a decimal place, that means you cut at the last non-zero digit. So this would be 3 sig figs. So if we were to be writing these two numbers using scientific notation, we would write them in two separate ways to indicate the different number of sig figs. So this one without the decimal point would be listed as 1, 2, 3, 4. So 3.42 times 10 to the 4. Whereas this guy with the decimal place would be listed as 3.4200 times 10 to the 4. Okay? And so those trailing zeros now indicate that these two zeros are significant, whereas they have been omitted from the top that does not include the decimal place. Okay, so next we are going to focus on our significant figure rules when doing mathematical manipulations. And so we have two sets of rules corresponding to whether we're doing multiplication division or if we're doing addition and subtraction. So for multiplication and division, the final answer has the same number of significant figures as the lowest original measured value. So for example, if we're doing the problem stating that 278 miles per 11.70 gallons. Okay, so if we're doing this division problem here, first step is to identify how many sig figs we have for each. So these are all non-zero numbers, so that's 3 sig figs in the top. On the bottom, this is a trailing zero after a decimal, so we know that is significant, so 4 sig figs. So when we do multiplication and division, we know that our final answer is going to have the same number of significant figures as our smallest value that we are multiplying or dividing. So since this 3 sig figs is the smallest value, we know our final answer has to have 3 sig figs. So if we plugged and chugged this math here, we get an answer of 23.76068 miles per gallon. And we know we need to cut this to 3 significant figures, which is right here. And then in a few slides, we'll go over our rounding rules, but this would now go to 23.8 miles per gallon in a proper number of 3 significant figures. Next, for addition and subtraction, the final answer has the same number of digits to the right of the decimal point as the lowest original measured value. So if we're taking a look at 3.18 grams plus 0.01315 grams. Okay, so we start off, this number on the top here, we know has 3 sig figs. This one on the bottom, we don't include our leading zero, so this has 4 sig figs. Okay, but the number of sig figs that they include here did not have, so the total number of sig figs doesn't have a bearing on the final answer's number of sig figs. It only has to do with the position of the final digit as related to the decimal place. So we know that our final answer is going to have an answer that's 2 places past our decimal point. So if we plug and chug our math here, we have 3.19315 grams. And so we're only going to include the first 2 decimal places. So our final answer, 3.19 grams. Okay, and that answer there has 3 significant figures. Okay, next we work through our rules on rounding. So first off, if the first digit you remove is less than 5, then you round down by dropping it and all of the following digits. 2, if the first digit you remove is 6 or greater, then round up by adding 1 to the digit on the left. And 3, if the first digit you remove is 5, and there are more non-zero digits following it, then you round up. Okay, so our cases here, if we say 8.767, and we're rounding to 3 sig figs here, since this value here is greater than 5, then we're going to round up. So this will now turn to 8.77. If we have a number 8.342, and we're rounding that to 3 sig figs again, since this number here is less than 5, we're going to round that down to 8.34. So rounding down means we do not change that digit. Okay, and our rule with 5, if the first digit removed is a 5 and there are more non-zero digits, then you round up. So if our value is 7.335 and we're cutting to 3 sig figs, since there's no more non-zero digits here, we're just going to keep it as is, 7.33. Whereas if you went 7.3351, since there is another non-zero digit, we're going to round that up. So that'll be 7.34. Okay? So those are our rounding rules. All right, next is dimensional analysis. So dimensional analysis is a method where a quantity described in one unit is converted into an equivalent quantity with a different unit by using a conversion factor to express the relationship between units. So you have an original quantity that you convert to an equivalent quantity using a conversion factor. Okay, and these conversion factors are going to be relationships. So for example, we know 1 meter is equal to 39.37 inches. And you can write that conversion factor in either way. You can write it as a fraction with the 1 meter is equal to those on top in the numerator and inches on the bottom in denominator, or inches on the top in the numerator and meters on the bottom. Both of these are equal to each other, and you can use them in any way that you want. So conversion factors are effectively equal to 1 because the quantities in the numerator and denominator are equivalent. So it's a way of converting the unit of an original quantity into a unit of a different unit by multiplying by essentially 1. So in general chemistry here, I contend that we don't actually do math at all. We're simply doing conversions. We're converting one unit into another. And so a lot of students have barriers put up about chemistry and science because they say they're not good at math. And so I believe actually that we're not actually doing math. For me, math is you're not doing math until you start to introduce integrals and derivatives. Here we're just doing conversions. Okay, so these are very simpler sort of relationships. So let's go through an example of a dimensional analysis problem. Okay, so I asked you, a man's height is 69.5 inches. How tall is he in meters? So first off, we need to determine what the conversion factor is between inches and meters. So we can look that up and find that 1 meter is equal to 39.37 inches. So how do you express a conversion factor? So in the previous slide, it showed that we can express a conversion factor as a fraction. And so we can write it in either way. 1 meter is equal to 39.37 inches, or we can flip it and say that 39.37 inches is equal to 1 meter. And so now we can use this conversion factor in order to convert one unit into another. So we start with our measured value over 1. So we always start with our measured value, 69.5 inches, measured value over 1. And so to convert from one unit to another, in order for a conversion to happen, you have to have the same unit present in the numerator and the denominator. So for us to cancel inches, we need to have inches on the bottom. Okay, whatever's left in the either numerator or denominator that has not been canceled out are what units are going to be in our final answer. So if we want to convert inches into meters, we know we want to cancel inches and we want to leave meters, so our final answer will have meters in it. So we choose which conversion factor has meters on the top and inches on the bottom. So we find this conversion factor on the left. For every 1 meter, we have 39.37 inches. So we can see our inches cancel out, and we get our final answer, 1.77 meters. Okay, and so we've noticed here that our final answer has 3 significant figures. And the reason is because our measured value that we started with also has 3 significant figures. Okay, so we would be able to tell if we did this incorrectly. If we use the incorrect conversion factor, we would see that our units don't cancel out. For example, if we say 69.5 inches, measured value over 1, and we put the inches on top, 39.37 inches over 1 meter, we see that our inches don't cancel out, our units don't cancel out. What would be left with would be an answer, 2,740 inches squared over meters, because these inches would multiply together to give you inches squared, and then meters on the bottom. So inches squared over meters is not the unit that we're looking for. So that's a way to tell that we have messed up this conversion factor. So this process of dimensional analysis, I know a lot of our stronger students are not going to want to do the work to actually write out all of this dimensional analysis, but I am going to require it. It's extremely important in order for you to keep good bookkeeping when we get to more complex problems. Okay, another problem that we might have here. Tungsten, the element used to make filaments and light bulbs, has a melting point of 6,192 degrees Fahrenheit. Convert this temperature into degrees Celsius and then into Kelvin. Okay, so what we need to do here, again, so this could be a dimensional analysis problem here, or a conversion problem. We're going to be converting Fahrenheit into Celsius or Kelvin. So for those, we need to find the conversion factors for each. So we know that degrees Celsius is equal to 5 degrees Celsius over 9 degrees Fahrenheit times degree Fahrenheit minus 32 degrees Fahrenheit. And then we also know that Kelvin is equal to degrees Celsius plus 273.15. Okay, so if we're going to solve now for our degrees Celsius, we simply just plug and chug our value into our conversion factor. So our temperature in degrees Celsius will be equal to 5 degrees Celsius over 9 degree Fahrenheit times, so we can just write times as a open parenthesis, our temperature in Fahrenheit, which is 6,192 degrees Fahrenheit, minus 32 degrees Fahrenheit. So when we plug and chug here, in our order of operations, we want to make sure we do our addition subtraction first, and then we can do our multiplication and division. And so we get a final answer of degrees Celsius is equal to 3,422 degrees Celsius. Okay, 4 sig figs, just like the value that was given to us. And then finally, we can now solve this for Kelvin by using our other conversion factor. Kelvin is equal to 3,422 degrees Celsius plus 273.15. And we find that our answer in Kelvin is equal to 3,695 Kelvin. Okay, so simple conversion factors to do some chemistry related math problems. All right, that's it for the day. Thank you.